we start? Thank you. Hi, welcome. I've never seen so many students. No, maybe the exam, but yeah, I'm glad you're all here. Hello, welcome. So this is the robotics systems control. I came to the right room. Yes, I hope you do. And yeah, today we're going to have like a short introduction. I will explain you who am I, what are we going to talk more or less the whole semester. And we will have like the first part of the theory, so that next week we can start with the labs. We already had, all of you, laboratory, some of you with me. So let's see what this course will all be about. Yeah, I will record the lectures. I mentioned it in the lab I took on Monday. Don't be afraid, I'm not trying to, I don't know, record who is here or whatever. I just, last year the students said that it might be a good thing to have. And it's a nice challenge, so I thought I'll try it. I'm recording the video, I'm recording my voice, and I'll also record the slides, so I'll try to make like a nice video that you can see the slides, you can hear the voice clearly, and you can see also the board. If you want to help with this, Joanna, the tutor that's taking care of some labs, will help with the recordings and stuff, but if you are interested in, I don't know, video editing and stuff, you can help as well, because it's a pain in the ass always to put everything together. I cannot promise it will be like very soon online and everything, but at least for the exams it will be there. But I'll try to make it like on the same week, so you don't have any excuse at the labs not to know the theory. Okay, that's the real reason. Okay, so yes, I should put it a bit lower, whatever, it's okay. So yeah, robotic systems control, it's just an introduction. Where we're gonna see, okay, what we're gonna talk, some history of robots, what kind of robots, robotic systems we're talking about, overview of the course. Hi, Joanna. Come on, go. It's already recording. If you want to move it around, right? I think it's recording. Yeah. So we're gonna see what types of robots there are and what kind of things we're going to see at the course, and some practicalities, and I'm sure you have questions about the exams, about all the little things. Okay? At any moment, if you have questions, just interrupt me, raise your hands. I'll try to get to know you by name. It's difficult since I'm not going to do the labs, but I'm trying. At least by first name. Okay, so you should know my name. This is my name. And as you can see, I'm probably not from Romania. I'm from Greece. And the first thing you should know about me is that this letter and this letter is the same for me. So sometimes you will see I write alpha, A, whatever. I get confused. I'll try to stick it to the left one when it's not meant to be the right one, but don't be confused, okay? That's the first thing you should know. I studied mechanical engineering at Aristotle University in Thessaloniki in Greece. And yeah, then I did my PhD in Belgium in KU11 in biomedical engineering, and now I'm working since 2016 at the Robotics and Nonlinear Control Group here at STU, this department. Our laboratory is at the Robansky, where you have your laboratories. It's that room and the room upstairs. Okay, so robots. Let's talk about robots. Where does the word come from? Every word comes from the Greek, but not robots. Robot is actually coming from Czech. Do you know about where is the word robot coming from?
From a theater place in Czechoslovakia in the 1920s.
Mm-hmm. And it was like it sounds like rabota, which is the Russian word or Slavic word for work. Yeah, and it was like a company that was making like mechanical slaves for people or something like this. I haven't seen the play, I haven't read it, but yeah. So that was the first time they used the word actually. And then Asimov, maybe you know about him, another writer, described the 3 laws of robotics, of robots, but still no robots around. It's just only in fiction, in plays and in books. And the actual first robot appeared in '56. It was called a Unimate, and I hope the video works. Yes. And it looked like this. Like big news.
That's its movie term. That's the immature reporting. A robot for industry. And this is it, Unimate, a machine that can reach out to 7 feet and perform a multitude of tasks in a factory or laboratory as skillfully as a man, but without getting tired. It's controlled by a built-in memory system. You just lead it once through the required motions, and it can then repeat them 24 hours a day, week after week. It can position objects to within 50,000 of an inch. Completely unaffected by heat, cold, fumes, or dust, it could take over a lot of unpleasant jobs. It can operate unattended for 500 hours. Originally developed in the States, it's now being made in Britain, and this was its public debut. Have one with me.
And of course it serves drinks to rich people.
The largest helicopter in the world.
That's enough. History. Okay. So, yeah, that was 1956. That makes sense. Yeah, as you can see, it doesn't look so much different than modern robots. It's the same thing, you know, the robotic arm that does stuff. Okay. But of course, more things got developed since then. There is something that was developed in '65 that we'll start learning about today, these homogeneous transformations, okay, like a mathematical way of describing robots more clearly and more precisely. We send robots to space with Viking 1 and Viking 2, and we send them to more space. Hi, welcome. So not just on outer space, but also on other planets. We send robots on Mars, on Moon, and other planets. And last year, not last year, 2 years ago, we had the first backflip of Atlas. Maybe you've seen these kind of videos. This is already old. There was one other video last week. I'll show you next week. I didn't have time. Have you seen this? Yeah. So from that thing that serves beer to this, come on, yes, in 50 years, 60 years. Hello. That was in 2017. And it's already old news. Like, as I said, there was another video from the same company, the same robot doing parkour and other complicated things. Right? Okay, so where do you think robots are used? Where do we need robots and why do we study them? What kind of applications or industries or
environments that are dangerous for humans.
Okay, that's good. Definitely, because
Medical applications.
medical applications. Why?
Because robots may be more precise than humans.
So when precision is needed,
Yeah,
right?
consistent.
And
Yeah, more consistent.
more consistent, yeah.
Factories for speed.
For speed. So when humans are slow or not precise enough, or it's too dangerous, yeah.
Or the work or the job that the human has to do is tiresome.
So repetitive work
Yeah.
or very tiring, yes. And one more thing.
Cheaper than hire a person.
Sorry.
Cheaper to by a robot that is
Right. That's always the case, I think. Maybe. Maybe not yet. Okay. Yeah. And one more thing. So one more thing is when sanitary reasons. So a human might contaminate, I don't know, food or something else, right? So several applications that robots are currently used is welding, assembling, packaging, food industry, yeah, other special applications, sorry. So yeah, medical applications that you mentioned, surgery, robotic surgery is becoming very, very popular, and so on and so on. Okay, so what kind of robots are there and what are we going to see? There are these type of robots called Cartesian coordinate robots, where basically they just operate on a plane, okay, and slight movements on off the plane. So for instance, this is some kind of sorting machines, okay, where they here, what's the benefit of a robot over a human? I guess speed. As you can see, they move really, really, really fast, and they put each object where it should go in a very precise manner, right? If you want this a person to do it, or three persons, just to be fair, okay, because here we have three robots. It's not an easy task. Okay. So these robots operate on a plane mainly. That's why they call the Cartesian coordinate. There's another type called cylindrical robots. That basically has to do with the area that they can reach. The area they can reach is a cylinder. As you can see in this example, I think this stopped working. Yeah. Don't worry, I have a beamer here. So, yeah, here you can see that the space that the robot can reach is basically a cylinder. Or there are other types which called polar robots, where the space that the robot can reach is actually a sphere. This is similar to the first robot that we saw, the Unimate. Or slightly more complicated robots. This is the main type of robot that we're going to talk about, is articulated robots, or another way to call them is robotic arms, because they look like an arm. Okay, they have a lot of joints in different configurations, and they can reach different positions in space. Okay. Besides this type of robotic arms and so on, also in the category of robots, it's the wheeled robots. There are robots with 3 wheels, with 2 wheels. I guess you've seen this kind of self-balancing robots like the Segways, even with 1 wheel. There is the robots that are with legs, like with the hexapods, they are with 6 legs, or quadrupedal robots. So this is also by Boston Dynamics. It has like 4 legs. There are even other robots that look more like humans. They have 2 legs and 2 arms, or different combinations. You know, up to your imagination. Or hybrid robots, where they have wheels, they have hands, or they have legs. I don't know if you've ever seen something like this. Basically, you know, it's a wheeled robot, but it also has legs. It can use the legs as arms, different configurations. It can spin, it can jump, it can go around. Now, if you are control engineers, so you know about control, so you know how difficult these things are to actually control. No problem. So yeah, they can do the shopping for you. Climb down stairs and so on. Anyway. Different terrains, they can jump over obstacles. Anyway, this is a frontier research. Actually, it's already old. You can jump. Another slightly more basic robots are the hybrid ones. The parallel robots where there is like a platform and you control the position and the orientation of the platform. Or even swimming robots, because all the things we saw until now it's on terrain. But they can also go in the water and why not also in the air. Drones. Drones are also considered robots and they are studied in the field of robotics. So you see the field of robotics, yeah, it's very, very big. Different kind of robots that we're studying. And that's just part of it, because in robotics, it's also considered vision and image recognition and so on, because the robots sometimes have to understand what the environment is, what is in the environment, and how to grasp items. So you also have grasping techniques and control methods and a lot. Now, in this course, we're not going to see all these types of robots. We're mainly going to focus on articulated robots, so robotic arms. We'll see a lecture on drones to see how they're actually working and how we can control position, orientation, and all these things. And we will also have a lecture on wheel robots. So again, how we describe them, how we model them, how we control them. Okay? That's just an overview. But as I said, we'll mainly focus on this kind of robots, the industrial robots. Okay? So, more exact what topics we're going to see. We're going to start with some mathematical background. It's not very heavy. It's very, very basic mathematics that you need. You need some linear algebra, basically. We're going to work a lot with matrices, if you remember, and multiplication of matrices. You remember matrix multiplication? We're not going to do it on hand all the time, but you have to understand, okay, what is it, how does it work, and so on and so on. And we will work a lot with coordinate frames. We actually start talking about this today, coordinate frames. Yes, so this will be our background that we'll start building. And then we will start talking about the kinematics of the robot. What is kinematics? Anybody knows? How would you understand kinematics?
The study of movement.
Of movement.
And the forces.
And the forces? Are you sure? No. Yes. Forces or not forces?
No.
Who says forces? Yeah, it's obvious. No. Kinematics is not about forces. Okay? Kinetics is about forces, which is the fourth bullet. You see? It's a very tight, small difference. But yeah, kinematics is just about position. And it's actually not about movement even. It's just about, static position. We don't care how we reach there and so on. It's just, I am there, I describe the position. Okay? So basically here we will start saying, okay, if I can control the joints of the robot, how can I know where the robot is in space? Okay? And the inverse. If I want to go in a specific position in space, what joints, how should I move my joints? And this is the inverse kinematics. So kinematics is, I know the joints, what is the position. Inverse is, I know the position, what are my joints. We'll see about this stuff, don't worry too much. This is one lecture by itself. Okay? And then we're going to talk about dynamics and kinetics, basically. Okay? So kinetics includes the movement and what forces produce the movement. Okay? So we'll start describing a robot with a dynamic model, okay, where we'll have input forces or torques, and we're going to have an output as the position of the robot over time, okay, dynamically. Now, once we have a dynamic model, you are automation engineers, or you will be next year, hopefully. So what we want to do is control the robot, right? We don't want the robot to just move randomly. We want to control the position or the speed or the force that the robot applies so that we can do all these nice applications we want to weld or move and stuff. So we're going to see several control strategies. using the dynamic model to achieve a certain position or a certain movement. Now, in order to apply the control, we will discuss a little bit about programming, embedded programming. Because in the laboratories, you're going to do some practical work with some embedded platforms, so we will implement the controller in the platform and then do a simulation on the computer. Okay, so we'll have to talk a little bit about embedded programming, but probably very few things. And yeah, once we have the controller, how we do the simulation and how we implement the controllers that we saw above. We're going to talk a bit about drones, as I said, and yeah, here I should add mobile robots, the wheeled ones, and a few things about sensing, like how does the robot know its environment, about planning, so how can the robot plan a course in order to avoid obstacles and so on, and then a few things about actuators, so how do we implement, what kind of actuators robots use. And one new addition this year will be, we're going to talk about ROS, which is Robotic Operating System. It's a framework that is very, very popular these days for implementing robotic systems, basically, for integrating different sensors and different methodologies for moving, planning, and so on. I thought if it's a robotics course, we should definitely talk a little bit about this, and we'll also try to have a lab this year. Okay, any questions here? Anything else you would like to learn about robots that maybe I can include? If you think about it right. Yeah, I forgot to mention that this might subtract. Yeah. Now, on the practical thing of the evaluation, the things are simple. We're going to have an exam at the end of the semester, and also a test for the laboratory, so like a colloquium, how you call it. The exam counts for 70% of the total grade, while the laboratory test counts for 30%. You don't need a 5 at the lab test to go to the exam, whatever, it doesn't matter, the total has to be above 5, so you pass the... Okay? Participation in the laboratory is obligatory, I guess Jan already told you. If you've been last week, and you should complete all the exercises. So this is a constraint for MA. Okay? I see people laughing in the back for the laboratory. Yes. So if you don't have any more questions, then we can start discussing about the first part. And if at any moment a question appears, right. One thing I forgot to mention is that all the slides and the information for the course and the laboratory exercise as well, I have them all on my website. You can find them. No, you see, I write alphas already. So this is my website. You can find course robotic systems control. Yeah. Is it here? Yeah, I keep on updating the presentations. At the moment I have the ones from last year. There shouldn't be any big changes, but you can always see at the first. So you can see here the first slide when it was last updated. So you can see if it was updated this year or last year. The material will be mainly the same, but maybe there were some errors last year that I need to correct, for instance. some small indices and stuff like this. Okay. But you can already see the material from last year. I don't know if you want to prepare before you come to the class. No worries. And yeah. Okay. Good. So I close this. Okay. Can you maybe stop the camera and start again? So we know. Okay.